An apple always falls towards the earth, but why?
In this video, we want to see how the bending of time around a large mass such as Earth makes objects fall towards them. As you know, the classical physics by Sir Isaac Newton explains the falling of an apple towards the Earth by the famous gravity law, where the pulling force is proportional to the product of the two masses and inversely proportional to the distance between their centers. However, Albert Einstein and his theory of general relativity explain falling of the apple very differently. Einstein teaches us that the apple falls because it's actually fixed in space but is traveling through time. The fall occurs in fact because the time is bent around a massive object such as Earth. Equivalently, we could say the apple is fixed and the Earth is accelerating upwards towards the apple. Strange, right? This can be explained by this geodesic equation. To understand this, watch the upcoming explanation by Dr. Nasser P.
I want to begin with very basics. These basics have almost not even directly to do with theory of relativity, but just want to make a sketch where we can make our ideas palpable. So here I want to show just the space-time in a very, very simple way. Space-time, I mean the like it is like a movie which are inside. We are all playing inside, but this is space-time is just one-dimensional. I want to name this axis time and this axis position. So then you see that we have just a one-dimensional position. Of course, position is three-dimensional, but this is just for making the explanation easier. It is still no relativity, you know. It is like you have position and time, and well, just consider like there is something like an apple here. I draw an apple. It's a very beautiful apple. And for example, if this apple is not moving, I could like sketch its trajectory in this diagram like this. Yes, so it is like a straight arrow upwards. This diagram is showing that position is not changing for this apple versus time. Interestingly, when we now think of relativity theory, instead of time, we have to write here special time. Why do we write a special? Because in relativity, time is nothing absolute in contrast to Newton's theory. A special means here for the frame from which I am observing this apple. Like if I look this apple from, for example, let's to make it a little simple. Let's say I am in space far away from the Earth and observing the Earth by a huge telescope. Why I want to be on space? Because I want to be somewhere far from every big mass like Earth or whatever that warps and bends the time and space. So I want to be in a so-called inertial frame. So let's say, for example, I'm in a space and I'm observing this apple, and then I see its trajectory in this diagram like this. Now just consider the that this apple is moving, like it is moving in position with a velocity. And the very interesting thing about special relativity is that it says that when I think I don't know what I explained there. I mean, this arrow that it is moving just in time. Okay, so this, when the position is fixed, it is moving in time. According to relativity, it is moving with the speed of light in time. So we are all of the fixed things in the universe are moving with the speed equivalent to speed of light in time. But so the time that is passing for you has this speed. It is really like this. But so why are we not moving in space with this speed? Because we're just fixed. As I said, we're not moving in space. But all of us are moving with the speed of light in space. But the theory of relativity has something very, very interesting. It says that if you have a speed, like for example, let's show it with v1, velocity 1, then the arrow sum of this your speed into the time and your speed in the space will be the same thing. So if the apple starts to move in this direction, it will have, because as I said, so here the length of this is c, but now the apple cannot move in time with the same speed. So this arrow sum will be also c, and now you see that the apple has indeed not moved in a space, in time with the same velocity as a fixed apple. Therefore, we see that having a velocity, of course, when the velocity is low, this is very, very, very small compared to this, and then the arrow will be almost at the same place. But let's say, for example, v is now as we are seeing here, even you can see it, v is now like you see it on very simple diagram, it is almost 2/3 no 1/3, sorry, 1/3 of the velocity of light, or actually more, it is 1/2 of the velocity of light. And you see now with 1/2 velocity of light, it's still, I mean, the time is still passing a little slower. Okay, so it hasn't been that dramatic effect still, but I just want to say that, you see, what I mean is that for this moving apple, the time is passing slow. Okay, but why am I showing this diagram? Because I want to show you something else actually, and that is, I want to switch. Now you see what the passage of time means. Now I want to switch actually to the stationary state near the Earth, and that's very, very amazing part that is coming. So just let's put space, or actually I don't know, I mean, I have seen elsewhere in scientific books that they put Earth on a side, so I also don't want to take the risk to sketch the Earth on the bottom, so I just put the Earth here. Now, as we said, the nearer you be to the surface of the Earth, the time will be slower for you. So just think of two apples, one here, let's do something funny. I will draw a tree for you. I don't know if you remember in the elementary school or whatever, kindergarten, we drew these funny trees. And let's think of another apple here, and it is funny that it is in this direction. Let's look at it here. According to the general theory of relativity, the time for these two apples will not pass the same. So while this time is like this, the time of this will be longer. Oh, sorry. It should be just in that direction, longer. Of course, it is very exaggerated. What I made, it's just as exaggerated as makes me laugh, because it's not, of course, not that much longer. It is just a little bit, but we want just to show why, to visualize why the apple will fall in the end. Therefore, let's put it this way. The thing that you should think of it is that just think of a stationary point. Here, the distance between them is, for example, x, and here, but here it can't be like this, okay? So these two apples, I mean, if you have one apple on the tree and the other on the floor, their distance between them will not rise with passing time, okay? So that's for sure. So that comes actually the visualization of the general theory of relativity. The only way that I can now, the only way that I can have the same x here is that I have to bend my arrow here. It is very interesting, huh? And this is actually a way of visualization of this bending of time that that we were talking about. I want to just to put our coordinates again here, like I showed here. This is very practical diagram in the field of specialty and general relativity. So everybody in YouTube or in books explain with this, so I also picked that. So again, here is then here is then it's my diagram. I just want to make sure that I think it's okay now. You see. Anyway, here is a position, and here is time. Oh, again, please forgive me from this. This should be a 90 degree. I mean, I put it here 90 degree. I forget this one. So the only way, of course, it is not as simple as this. It has huge formulas behind it in the general theory of relativity. But the only way, very simplified, the only way that this distance remains constant is what? This should bend. So the time bends. This also bends actually. So, but still this bends. It's funny. This should bend more than this because it is nearer to Earth. But in the end, because this one is longer, even its less bending causes this x to remain a constant. Something like this. Like just think of this. That like this time arrow bends, and then this also bends. Maybe even not as sharp as here. You see this angle is smaller than this one. And then, but they bend in a way, this time bends in a way that the distance between the apple after, for example, doesn't change. So this x we have also here. Now you may wonder why this is into the earth, but it is. I mean, it is into the earth. That's nothing. I mean, it's not a position. It's just time. So this is very, very simply and oversimplified manner, and not very accurately an explanation why the time is bending near the earth. But just look at this one. Very interesting is that I am holding via a force the apple here, and if I hold it, it will have this constant x from the earth. I mean, so this x will remain constant. But as soon as, let's say, I make the apple loose, according to the general theory of relativity, there is no force. So I have made the apple loose, then it's in a free fall and there is no force. But what will still happen? This loose apple, funnily, will be in, how do you say it? It will be in its inertial path. So actually it will be like here, it will be just moving with its how do you say, initial velocity in the direction with the same in the direction of the time. And it is actually here, this apple is fixed, so if you don't exert any force, it will just move in the time direction with the same velocity of c. And interesting is that if I make this apple loose, it is now in now no force is exerted to it, so it will behave the same way that apple here is behaving. It will be moving in the same direction, parallel to the axis of time. Funny thing here is that the axis of time here is warped, so it's interesting, huh? I mean, it's so if we cut it loose, it will, of course, it will move parallel to the axis of time, and also actually its position doesn't change, because please don't mix up this distance with the position of apple in the space. You know, the position of apple in the space is not its distance from Earth. It is a position. I mean, actually, a better definition for it is that a fixed position be parallel. A fixed position be when the apple is like moving parallel to the axis of time and is not moving in any. It doesn't have any speed compared with an inertial frame in the space. So this you should not take as a the apple is changing its position. No, it is fixed. The apple is fixed, but it is moving on this curve that will finally lead to the Earth. The funny thing is that it also looks that the apple has an acceleration, because if you look at this, you see that the derivative means the slope of the tangent that I sketch to this curve. This derivative is getting higher and higher. Actually, the change in derivative, I mean, it's the derivative is the velocity, and the change of it is the acceleration, and this form shows like it resembles, this behavior resembles an acceleration of, in this case, g. So g will be the change in velocity for a certain amount of time. This is speed, time, and this is g. And very amazing. I mean, it's we actually have found like a logical way to explain why the apple is falling without a force being there. And now it is also interesting to say that you have seen, of course, maybe in many literature that they also explain it with the fact that Earth has actually I mean, in literature, falling of apple is explained by the fact that not the apple has an acceleration towards the Earth. This is also, actually, we also agree with this. As I told you, the apple is fixed in position, but it is moving straight in the time direction, and so it hits the ground, but it doesn't really have an acceleration. It looks, if we look at this distance as the position, which is not the position, is the position here is just a fixed position, is when you just as I said, just move on the arrow of time in the same direction of arrow of time. So we also said that, but what I said was that it just looks like an acceleration. So an acceleration would also look, if the Earth would have had a gravitation which would have been exerted on the apple, it would have the same trajectory. So I want to correct if I made you, if I confused you. Again, there is no acceleration. It looks, this curve looks like an acceleration. If we take this distance from the Earth as the parameter for indicating our position. But we can also say it the other way. We can also say it that, okay, the apple is fixed, but we can also say that the Earth is not fixed. Why it is not fixed? The Earth is not fixed. We can say the apple is fixed. It is here, as I said, it is moving on the arrow of time, which in this case, if we have the Earth like as a, if this have the surface of Earth as a reference, it would look like the apple is going down to the Earth, or we could see it the other way around. Let's look at this like the apple is fixed. It is in the space fixed because it is on its arrow. This Earth, look at this. Look at this apple, for example, that is on the Earth. Or let's call it something else. For example, a bush. Let's make a bush. this bush is actually moving in space. Why? Because it is not following the warped trajectory of time. So if I come back here, it is like if I make, look, if I make my arrow of time here straight, this bush is like having this trajectory in the versus the position axis. You see, it is having, actually it is accelerating. If I make this thing straight, the bush, we can say, is accelerating in relation to this straight arrow of time. So actually we can say that the bush is, we can make everything reverse all of our references. We can say that the apple is fixed, and we can say that the bush is like having an acceleration upwards. And this is also how we can explain this thing that you may read in many places, and you may wonder that they say actually when an apple falls, according to the general theory of relativity, it is the Earth that is having an acceleration upwards. It's also a way of explaining it, and it's right. So we also showed that if we look at it this way, because the time is bent in that direction, our bush is now, because the time is bent, our bush is now going upwards. This upwards, of course, we cannot see, because actually the bush is always in the same surface versus time, but the point is that this surface, this fixed surface, is not the fixed surface in relation to the arrow of time, but it is just a fixed surface that we have in our minds and in our brains. For us, constitutes the surface of the Earth. And it's also right, it is of course sensible to look at it like that it is fixed, because anyway it is not moving in that classical way of thinking, but it is actually moving because the time is warped. And one other thing is that this warping of time is has the in our world the only effect that it has is like causing this falling of an apple, and you actually do not see, for example, time difference, a real time difference from here and here. If you, for example, put a clock here and here, that time difference will be minimal. So actually I'm done, and I hope that you have understood this very complicated concept of a general theory of relativity. And so I hope that you will visit my page again and be tuned up for my next videos that I want to put about very, very interesting topics. And please come again, and please subscribe to my videos, and also please press that bell button. Okay, thanks a lot for your attention.